Okay, so there are three methods of heat transfer. And the first one we're going to look at is the method of conduction. And he gives us a good illustration of what that would be. And say you had a metal bar, say this long, and you're holding this end up here, and down the bottom of this metal bar of iron or copper or whatever, I have a candle, and it's burning, and that flame is supplying heat to that metal bar. Initially, where I'm holding it up here, it won't be hot, but eventually, as I apply that heat, the atoms vibrate, and that vibration is transferred progressively up the bar. At some point, I'm going to have to let go of that bar because it's going to heat up at that, at some point. And that is basically what we term as conduction, heat conduction. So here is that situation, right? This metal rod, candle flame, eventually, we will get to the point here to where the top of this metal rod will get very hot through this process of conduction. Now, the rate of this heat transfer from here to here is dependent upon the thermal conductivity of the material that it's composed of. Copper is a better thermal conductor than steel. Plastic and non-metallic materials are poor conductors of heat. So there's an SI unit of thermal conductivity, and it's the watt per meter degree Celsius. Okay, what does that look like? Well, that looks like watt degree meter degree Celsius. Again, another one of those things that we don't have to derive, we just want to use. But what we want to know from that is this is a measure of how fast heat can be conducted through a material. And as was with the specific heat capacity, we have a table that we can reference to find this value. So let's look at that. Let me show you where that is again in our appendix, and we'll work a little problem on heat conduction. Okay, so again, looking at the appendix in the back of our book, this one, we've actually got two tables. One is AX1, which is the property of insulating materials. And of course, what we're talking about with insulating materials are materials that are not thought of as good conductors of electricity. Okay, and then we have already used table AX2, which is an electrical, mechanical, and thermal properties of some common conductors and insulators. So there's two separate tables that we reference. But for this thing, and I just want to show you this because we're going to progress over to this problem here in just a minute. But the one that he's going to reference to us, and let's see if we can make sure we know which. All right, so thermal conductivity, and let's look at the one that we're going to use in our example. Oops, not all of these, but we're going to look at mica. Well, I can't get it to just that, but it shows us that the thermal conductivity for mica is 0.36. Okay, what does that mean? Okay, 0.36 watts per kilogram degree C. And again, this is going to give us a measure of how well this material conducts heat. And again, there's a lot of these, and you look at mica, and of course mica's not a good electrical conductor. If I go down here to copper, and I look at copper, and I look at its thermal conductivity, we see it's a 394 watts per meter degree C, watts per kilogram degree C. And you see a big difference between something that's considered a conductor and something that's considered an insulator in regard to its thermal conductivity. So back to our specific problem, we're going to have this equation, which is 318, which is the equation for thermal conductivity. The P represents power. The Greek letter here that I can't think of the name of off the top of my head is this thermal conductivity of the body. And the A is the surface area in meters squared. Temperature 1 is the difference in temperature between the opposite faces of the thing that we're looking at in terms of its conductivity. And the D is the thickness of the body in meters, okay? So this is what we're actually looking at in terms of this equation 318, where we're looking at these particular values across here, area, and then T1 minus T2, should have made those lowercase, and divided by the diameter in meters. Okay, so we have a problem that we're going to work using this and looking at this heat transmission by conduction figure. And on page 63 says the temperature difference between two sides of a sheet of mica is 50 degrees C. So, you know, on one side it's 50 degrees different than on the other side, okay? And so if the area is 200 square centimeters and the thickness is 3 millimeters, calculate the heat flowing through the sheet in watts. Okay, so we've got the formula to do that. Now, you know, we'll look at a couple of things here. First off, of course, he gives us the area is 200 centimeters squared. We need this in meters squared. So, you know, we're going to do that conversion, and you know, we all know how to do those conversions now. So to put this in the proper form to fit our equation, which needs to be in square meters, we determined that this would be 0.02 meters squared. And then the other thing is the thickness is 3 millimeters, and the 3 millimeters in meters would just be that about divided by 1,000, or 0.003. Okay, so that gives us everything that we need to know. Now back here when we were looking at the table, we came up with this value of 0.36 for this mica. And so now let's plug in here and see what we can come up with. Here's our formula, 0.36. Here is our area, and it's 0.02. Looks like we're dropping units. Temperature is, let's see, how do we know that? Well, he doesn't, it shows in one figure, but not the other. It shows us that the temperature here is 120 degrees, and the temperature on the other side is 70 degrees. And actually, I should be on this slide, shouldn't I? So this is what we're actually looking at to get these values. This is sort of a generic look at this idea of conduction, and here's our specifics here. Okay, so when you're working this problem, this is what you're actually looking at. I've already got the numbers in over here, so let's just finish this. This is 120 minus 70, and then that's all divided by the distance, the thickness in meters, 0.03, and the power, thermal power that we calculate from this is 120 watts. So if the area is 200 centimeters square, thickness is 3 millimeters, calculate the heat flowing through the sheet in watts. Okay, this gives us the heat in watts that is conducted through this mica. Just a quick example, and of course what you want to take away from that is equation 318 is our equation for thermal conductivity. conductivity.